This talk is a peek into the future where permissioned blockchain systems will be able to replace some of the database applications, and users will benefit from the logically centralized but physically decentralized data that is stored in them. The project is called StreamChain, and it's a collaboration with IBM Research. Already today, but increasingly in the future, many enterprise blockchain applications will be running in environments with access to fast networking and powerful multi-core servers. However, the existing systems cannot really take advantage of this underlying hardware to offer high performance. So what our goal is to reduce their latency, at the same time keeping their throughput high, and this way reach higher adoption of permission blockchain systems. The idea is to revisit the core processing of these systems and turn the block-based transaction processing into streaming one. And this enables new opportunities for blockchain, as well as the ability to benefit and keep on benefiting from new hardware trends. So before I explain how we implemented StreamChain, I would like to provide a background on blockchains. Public or permissionless blockchains are basically a data structure, a fault-tolerant append-only log. This means that participants can look at the data blocks, can look at the log and verify its integrity through the use of cryptographic hashes that link these elements together. The membership is open, so anybody can join and access the data structure, but what is more important is anybody can actually propose another block to be appended to the log. Participants are not trusted, so we can have actually malicious participants or even colluding participants. And to protect against the corruption of this data structure, what is being used is proof-of-work based consensus or similar solutions that require the members to solve a very expensive cryptographic puzzle before being able to propose a new block. The main use case of these systems is in cryptocurrencies. However, as we are all aware, the proof-of-work consensus has a very high energy cost, and here what you can see is that, for instance, Bitcoin, running the Bitcoin network consumes as much electricity per year as somewhere between Colombia and Venezuela's yearly electricity consumption. So in enterprise use cases, instead, we are looking at so-called permission blockchains, which at the lowest level rely on the same data structures and ideas of ensuring integrity. But in these scenarios, members are actually known. So we can rely on a trusted third party or a consortium of nodes or the existing members to authenticate new members in the network. Still, not all of them are trusted, so we need to use consensus methods that can protect against malicious members, but this can be cheaper and more efficient than proof of work or similar consensus. So in permission blockchains, BFT, so Byzantine fault-tolerant consensus algorithms are typically used. There's a large number of use cases that are being considered, including healthcare, notaries, supply chain management, and there's also countrywide networks such as Austria and Spain, and regional networks such as the European Blockchain Services Infrastructure that are emerging. Even though permissionless and permission blockchains differ in their membership model, the underlying design of how the systems are running and executing transactions is very similar, which is a problem because the assumptions and the environment that the systems run in are different. So if you look at permission blockchains, because of the high cost of proof of work consensus, they need to batch a lot of transactions together in blocks, this way amortizing the cost of the consensus algorithm. They're also fundamentally geo-distributed, and the whole system has to be designed around the high latency communication links and low bandwidth across nodes. So gossip, for instance, has to be used to reduce the bandwidth bottleneck on any single node, even if this comes at the cost of latency. Permission blockchains, on the other hand, don't require proof of work, so they can use more efficient forms of consensus. And there's emerging use cases where these networks have access to very fast networks and powerful modern hardware. So examples of this include countrywide networks like Austria, where the system is not geo-distributed, it runs in a more confined environment. Or other examples include cloud-based blockchain platforms where several companies might be deploying a blockchain network on IBM's or Amazon's cloud, running in a more controlled environment. However, the main problem with permission blockchains is that even when you run them on these fast networks, they take hundreds of milliseconds for transaction finality. So if you compare this to the state of the art of databases, they are at least 2 orders of magnitude away. So the reason for the high latency is to be found on the blocking processing behavior. So permissionless and permission blockchain both process transactions in blocks, which, as you can see in this illustration, will lead to artificial latencies added to the system at various steps in the processing pipeline. If we would switch instead to a streaming behavior where computation and communication is overlapping, we could actually reduce latency significantly without negatively impacting throughput. Now, the main challenge here is how to go from a block-based processing to a streaming-based one without actually forfeiting the security or reliability guarantees of these systems. To understand how we can bring streaming processing to these systems, let's look at their architectures. So they are composed usually of 3 types of nodes: authentication or coordination nodes, consensus nodes, and executor nodes. Now, in this illustration here, I'm showing logical roles for the nodes, which of course, depending on the actual implementation of the system, could be co-located on a single physical node. So I'm taking here a general view, but depending on the actual implementation, the naming or the grouping might be a little bit different. The authentication nodes, they can be either a trusted third party or a consortium of the nodes in the network, and they have as a role of authenticating and authenticating members and managing the network. The consensus nodes, or we can also call them the ordering service, combines transactions submitted from the executor nodes into blocks, and this way they establish a global total order. The executor nodes are the ones who actually run the smart contracts submitted by the client and record the results in the ledger. They can have either an execute order validate or order execute execution model. From the perspective of what we're proposing here, both types of systems would benefit from our ideas. So in StreamChain, we rely on some design principles to actually bring the streaming processing to these systems. First of all, we need to reconsider how transactions are processed at every node. And instead of batching them into blocks, we need to execute at the level of transactions. Now, this will reduce latency, and if done right, it will do so without impacting throughput. However, there are still elements in the systems, for instance, disk accesses that have a very high cost and need to be hidden in order to keep the performance high. So for this reason, we still rely on some amount of batching to interface, for instance, with the disks, but we decouple this physical batching from the logical batching of transactions for the purpose of recovery or metadata management. And then finally, what StreamChain does, it doesn't actually change the amount of cryptographic operations needed to run these blockchain networks. So in order to keep the throughput high, we rely heavily on multi-core parallelism to execute various signature verification or signature creation procedures. So implement the StreamChain on top of Hyperledger Fabric, which is an open source permissioned blockchain system. And we've done so without changing too much the transaction structure or the on-disk data structures. So overall, StreamChain is compatible with existing Hyperledger Fabric-based applications and would allow developers to try out their applications on a lower latency version of Fabric. So if we look at the performance numbers in a nutshell, what we see on this graph is throughput on the x-axis increasing to the right versus latency of the system. Of course, a lower latency is better. If we look at off-the-shelf Fabric as reported in the Eurosys paper, it achieves somewhere close to 4,000 operations per second with latencies in the several hundred millisecond range. In comparison, if we would have a naive streaming system where we simply configure Fabric to put a single transaction in each block, then of course we could reduce latencies a little bit, so by almost an order of magnitude, but throughput would suffer. So what we're proposing with StreamChain is to actually reduce latency by 2 orders of magnitude without impacting throughput too much. The reason that StreamChain doesn't quite achieve the throughput of Fabric is to be explained by inefficiencies in Fabric's internal data management, and is something that I will come back to later in the talk. In Fabric, transactions are executed in an execute order validate model, where clients submit smart contract implications to the executor nodes. This will simulate or run these smart contracts and determine a so-called read-write set, so a list of read and write operations on key value pairs that these smart contracts would perform. Once a sufficient number of so-called endorsements are collected, the transaction is sent for ordering, and then finally the ordering service sends blocks of transactions to the executor nodes that validate the read-write sets and commit the results to the ledger. This execution model is beneficial because it allows for a wide range of applications to be run. So in terms of smart contracts, it allows for higher flexibility, and the operations on the blockchain are, let's say, cheap, because it's only about inserting or modifying key value pairs. Now, one peculiarity of this model is that in order to be able to simulate the transactions, the executor nodes have to maintain a so-called state DB, or a materialized view, an up-to-date view of the key value pairs in the blockchain. And as you will see later, this can create problems because, of course, there is a latency associated with updating this state DB, as opposed to the transactions that are being committed to the ledger. So if we look inside the Fabric node, we can see that endorsement and validation happens concurrently, accessing the same data structure, which is the state DB. As blocks are received from the orderer, the validation pipeline will look at all the transactions within the block and verify their signatures in parallel, and then perform a large batch-based operation, flushing the results to the ledger, but also updating the state DB. What we do in StreamChain is to break up this execution into more pipeline stages and tweak it so that instead of block-based processing, they have a streaming processing where transactions, signatures of transactions are validated in a streaming fashion on multiple cores, and then also the state DB is updated not at the block granularity, but with each incoming transaction. Now, as I mentioned earlier, writing to the ledger, so persisting to the disk, is still a very expensive operation, and if we would do it for each transaction independently, then the general performance would suffer. Instead, what we do is we rely on batching to access the disk. While what I described before on the previous slide indeed reduces the latency of StreamChain, we faced two challenges when it came to ensuring that throughput stays high. One challenge has to do with the concurrent access to the state DB between the endorsement stage and the validation stage. Initially, in Fabric, there's a single global lock that makes sure that data is not corrupted in this state DB. But with StreamChain, where the validation step would update the state DB with very high frequency, we had to actually take a different approach and replace the global lock with multiple locks that protect only parts of the database. This way, we could have more parallelism in the system and actually achieve higher throughput. The second challenge had to do with hiding the disk access overhead, as I already mentioned. But what made this challenging is that within Fabric, there's actually several places where either an on-disk database or files on the disk are being accessed. And the approach that we adopted here is to batch writes whenever possible, caching some of the dirty data in memory and flushing it with some frequency. Now, of course, there's a trade-off here because there's a small window in time, so several milliseconds, where data is not persisted yet to the disk. However, because the system does persist transactions at the ordering level and also at the ledger with several members, we consider this trade-off safe enough for operational systems. Now that we've seen how StreamChain changes the way transactions are processed and how it separates the different processing steps into independent pipeline stages, we can look at a more detailed view on latency. So this graph shows throughput increasing to the right with latency on the y-axis. As you can see, all three large stages, endorsement, ordering, and validation, have similar latencies in the half millisecond range, and they behave fairly stably up to the saturation point of the system. If we think of transaction committing, which is the ordering step, and the validation together, with low loads, the system actually can do this in less than a millisecond. So what this graph shows is that high latency is not something that is fundamental to permission blockchains. It's simply a side effect of the execution model, or a side effect of the processing model that these systems have adapted. In terms of reaching higher throughput, the next step to improve would be both the ordering and the validation step, because at this point, they are the bottlenecks of the system. While StreamChain does reduce latency without impacting throughput too much in Fabric, there's another aspect that we have to look at, and this is something that is in general a problem in execute order validate blockchains. Namely, the fact that transactions can fail in the read-write set validation phase due to stale data in the StateDB. What happens is that there is a large time window between simulation or endorsement and actually committing the changes of a smart contract to the ledger. In this window, the changes of this smart contract will not be visible in the StateDB yet, so any other contract execution that depends or might conflict with the outcome of the earlier contract will be endorsed on old data and will fail in the validation phase. To overcome this, clients have to retry transactions or use some form of rate limiting. As an alternative, in some application scenarios, it is possible to replace the execution model or the programming model of clients with UTXO, but this is of course not something that is generally applicable. What StreamChain brings to the table here is that due to the reduced time window between simulation and committing, there is actually less staleness in the StateDB and less transactions will fail. Of course, we cannot fundamentally solve the problem of failing transactions, but we can alleviate the symptoms. So if we look at an actual experiment measuring the benefits of having a streaming-based processing in this execute order validate model, we can see here a YCSB workload, and we're plotting the number or the percentage of failing transactions on the y-axis versus, let's say, the load on the system. So here we're normalizing to the maximum throughput of Fabric with this particular workload and StreamChain with the same workload. We use two different setups, one with a very small hot set of keys, so only 1,000 keys are being accessed in the YCSB workload, and one with a larger one. As you can see with Fabric, once we have a hotspot in our workload and we are reaching higher throughput levels, the amount of failed transactions becomes prohibitively large. So in the 90% load or 95% load of the system, 1/3 of the transactions are actually rejected due to this staleness. With Fabric, we can actually, with StreamChain, we can reduce the staleness in the system, and we can actually achieve almost no failed transactions up to something like 97% load on the system. This means that running StreamChain in production would result in a more predictable behavior. And since, as you can note, the actual throughput achieved in this workload is almost twice as large in StreamChain and in Fabric, we can actually run today's systems with no failing transactions safely using StreamChain. To conclude, let's look at what StreamChain actually enables us to do. So most importantly, because we bring up latency as a first order performance metric and do this without reducing throughput, we can actually evaluate ideas with a decent performance. So we can take applications that today are run on traditional database management systems and port them to this permission blockchain platform and compare on a more level playing field. One example application that we explored is a supply chain management use case done by a student in our group, where the participants of the supply chain network benefit from the logically centralized data because they can actually quantify the healthiness of the supply chain. And this is something that economists, for instance, see as a very promising use case for blockchains. Overall, we can use StreamChain as a platform for further exploration. There is a lot of related work on increasing the throughput of permission blockchains, and all of them or most of them are applicable to be layered on top of StreamChain. And we can also use StreamChain as a starting point to explore further steps of reducing latency. So in StreamChain, all the pipeline stages have been separated. If one has ideas on reducing the cost of endorsement or the ordering or the validation, now the improvements will directly show up, which before was not the case. In Fabric, even if you would reduce the latency of, let's say, the distributed step, the ordering, the reduction in latency will not really show up overall in the end-to-end performance. If you're interested in more, take a look at our paper, which is on archive, and feel free to reach out to me with questions.